Laboratories, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have presenters from two Building America teams here today to tell you about retrofitting central space conditioning strategies for multifamily buildings. Our presenters will discuss hydronic heating methods and the evaluation of thermostatically controlled radiator valves, or TRVs. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin you should use to dial in. Panelists, we ask that you please mute your audio device while you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you would like to ask a question, please use the questions pane to type in your question. If you are having difficulty viewing the materials through the webinar portal, you may find PDF copies of the presentations at the website listed here, and you may follow along as our speakers present. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting agenda prepared for you today that will focus on improving the performance of space conditioning systems in multifamily buildings. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we will have a question and answer session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for nearly 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. Building America uses applied research to deliver building science solutions using a 4-step framework. These innovative solutions are tested in homes to develop proven case studies of success the market can point to. Building America provides the tools the building industry needs to ensure the innovations are applied correctly, always keeping an eye on energy performance, durability, quality, and affordability. The final step, infrastructure development, is the conduit to getting innovations to the marketplace. Building America research focuses on how the components of new and existing homes work together through systems integration. As the market changes and evolves, so has the direction of our research in order to add value and drive changes in performance across the residential building industry. In addition to technical challenges we have been addressing for decades, there is now a need to understand market transformation issues such as valuation of energy efficiency to our portfolio. In the nearly 20 years of Building America research, we have spearheaded combining ultra-high efficiency with high performance in both new and existing homes, and we are consistently achieving this challenging task. For example, in 1995, a typical home used 3 times more energy per square foot compared to today, and indoor air quality, comfort, and durability problems were common. Today, a home built to DOE Zero Energy Ready home specifications uses less than half the energy and is more comfortable, healthy, and durable. By 2030, Building America will demonstrate that new and existing homes can produce more energy than they use. Do you want to know more about these proven innovations born out of world-class research? The Building America Solutions Center is your one-stop source for expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. You can find it by the URL on your screen or by searching on Building America Solutions Center. And now on to today's presentation. Our webinar today will focus on improving the performance of central space conditioning systems in multifamily buildings. Presenters will discuss hydronic heating strategies and the evaluation of thermostatically controlled radiator valves. If you would like more detailed information about any of these efforts, or if you're interested in collaborating, please feel free to contact any of our presenters. Our first speakers today are Jordan Dentz and Hugh Henderson, and represent the Building America team, Advanced Residential Integrated Energy Solutions. Jordan is a vice president at the Levy Partnership, where he develops and manages building science research projects and consults for building owners and operators. Hugh Henderson is a founding principal at CDH Energy, where he researches technologies such as combined heat and power, cooling, and dehumidification in residential and commercial buildings. Today, Jordan and Hugh will discuss various control strategies to help improve hydronic space heating performance in 3 low-rise multifamily buildings in Cambridge, Massachusetts. In addition, Eric Antonelli is here to present with Jordan about research results of the effectiveness of thermostatically controlled radiator valves. Eric is a mechanical engineer at the Levy Partnership, where he specializes in steam heating systems. Representing the Building America Team Partnership for Advanced Residential Retrofit are Peter Ludwig and Russell Roosh. Peter is Director of Building Retrofits at Elevate Energy in Chicago, where he works to develop energy-efficient housing for building owners and renters. Russell is a Senior Energy Analyst at Elevate Energy and explores energy efficiency strategies for retrofitting multifamily buildings. Their presentation will focus on 3 studies that identify best practices, costs, and savings associated with retrofitting older steam and hydronic multifamily buildings. They will especially focus on the process of balancing these buildings through increased mainline air venting, improved circulation pump efficiency, and upgraded boiler control systems. With that, I'd like to welcome Jordan to start the presentation.
Thank you, Gail. This is Jordan. I thought I'd start by talking about why this topic is important. First of all, there's quite a large number of homes in the U.S. with space heating provided by steam and hot water, approximately 14 million. And in many of those homes, because they're in the northern climate, space heating is the largest energy use. I want to point out this study pictured on the screen was published last year, and it's on the Building America website, and it documents the extent of overheating in a sample of typical New York City apartments. I'm just going to give you one of the results from this study. Over 100 apartments in 18 buildings were looked at, and space temperature data was examined. Almost all were overheated most of the winter, and this was true for both steam and hot water. And while energy management systems reduced the overheating in many of these apartments, it did not stop overheating in most of the buildings. So this is the presentation we're going to talk about first, is the 3 buildings in Cambridge that Gail mentioned. And I would like to turn it over to Hugh Henderson to discuss the next few slides.
Okay, thanks, Jordan. Yeah, so in this field test, what we wanted to do was compare traditional boiler controllers and look at the impact of all kinds of all types of control strategies and see how they affected energy use. So for years, people have basically reset the supply temperature for boiler based on outdoor air conditions, and so that's one of the things we looked at. There's also new technologies to cut off, to use things like wireless space temperature sensors to look at the space temperatures and cut off the boiler based on that. And And along with boiler reset strategies, there's also nighttime setback strategies that can be used where the supply water temperature sent out to the building might be lower at night. And so we were looking at all three of these strategies, and we're looking at the way they've been done traditionally and how they've gotten better with the newer control, the newer controllers that have come out, and also the newer technologies like wireless. So the next slide, Jordan. So our site was a 3-building complex in Cambridge, Massachusetts. It had hydronic heat. There were 3 buildings, and you'll hear us talk. They were building 4, building 3, and building 55. And they had, and so some were behind the street, and some were at the face of the street. And they had from 9 to 18 apartments in each building. They all had well-McLean boilers. Each building had 2 or 3 boilers. There were TRVs on many of the radiators, but they had essentially failed. So when they fail open, so there's basically no control. They all had some kind of a reset controller, though some were very old-fashioned. And so what we did is we replaced those, and we took out the old-fashioned ones and put in better ones, and we also put in the wireless sensors and controllers that could take advantage of that. So the next slide, Jordan. So I'm going to talk about first site 4, and then Jordan is, or building 4, and Jordan's going to talk about 3, and then we'll come back to building 55. And so the setback strategy that the building originally had, building 4 had a newer controller, and really all we did was to change the parameters for the outdoor air reset strategy. So the blue line shows what the strategy was when we first arrived, and the green line shows what we changed it to. So what we essentially did is we lowered the minimum temperature, the minimum supply water temperature that the boiler could provide. And so things originally, so the supply water temperature had got up to 180 when it was 10 degrees outdoors, and then it decreased to about 130 by the time it was 48 degrees, and we never allowed the supply to go below 130. We had essentially the same thing when we installed the new controller, but it went down to 110. So next slide, Jordan. And so what we did, and so we looked at lots of behavioral things, but here's sort of the bottom line look at the gas bills. And so the monthly gas bill, so we made a very modest change to the setback strategy or to the boiler reset strategy for this building. And so you can see the 2 lines here. So what was there, but before we arrived is the red data, the 2010 to 2011 data, and so with the new controller shown with green, and we saw, and so really, and so the straight lines are a little misleading, and of course most of the difference is in the mild conditions with the setback strategy, and so we did see a noticeable change. On building 55, we're not showing that data here. We also saw we had a bigger change in our reset strategy and had even more savings. But this kind of shows you the idea. And we fit this data to a change point model. And in this particular change point model, we've taken out the water heating data and made so the y-intercept is 0 actually. So but obviously there's always gas use associated in the building with water heating, and then gas use associated with space heating. So the next slide, Jordan. And the results are, so we saw, so we also placed a lot of hobos in the various departments in this building, and just like, and kind of a theme that Jordan mentioned, and you're going to see, I think, in a lot of this is, so space temperatures in a building from unit to unit can vary on the
Hello, Gail. Shall I pick up from here?
Yes, please.
Okay. Hugh must have dropped off or something, so I'll pick up from here. This is Jordan again. So as Hugh was mentioning, space temperature varies quite a bit from unit to unit and over time, over the season. This is about 7 apartments or 7 sensors in that building. The bottom line, though, is that heating energy with the change in the boiler reset control decreased by 10%, and indoor temperatures are still well above 70 degrees throughout the season, and there, in fact, in actuality, is room to reduce it even further here, as you can see by the temperature data. We do have some data from the other building as well, in which case there was an even older original reset controller, and the change here produced a more dramatic savings. Similar graphs, the reset curve on the left you can see was changed more dramatically. The original blue reset line was quite a bit higher than the other building, and we brought it down to a level similar to the curve that was in building 4. And here we saw about a 15.5% energy savings. So now I'm going to move on to building 3, which is a study of the indoor temperature cutoff. And in building 3, we installed this system, also sometimes called an EMS system or energy management system, and it cuts off the boiler when the average space temperature exceeds a set point. And in this case, the set point was 73 degrees in the day and 68 at night. When that set point was not exceeded, the outdoor reset control was in effect. And we had 1 temperature sensor in every apartment in this case. We operated the system over the course of 1.5 heating seasons, alternating periods where the indoor cutoff function operated or it was enabled, and periods where it was disabled. And we had about 6 months of data under each case. 6 months where it was enabled and 6 months where it was disabled. And during that time, we were tracking the boiler runtime hourly. You can see on the right here is a table showing the average space temperature during the heating season. And it decreased by about ½ degree when the indoor cutoff was enabled. So not a huge impact on indoor temperature, neither day or night, on an average basis. However, we did find that at night, with the indoor cutoff enabled, the boiler hardly ran at all. And this is the load line showing the weekly periods using nighttime data only. Green is with the indoor cutoff active, so quite a bit lower lower boiler runtime. As a matter of fact, 71% lower during the night. So during the day, the indoor cutoff reduced boiler runtime by 1%, but at night it reduced it by 71%, an overall reduction of 28%. And these numbers mirror closely the percent of time that the indoor cutoff mode was active, that is, when the boiler was overridden. Our conclusions from this are that, number one, the outdoor reset was probably set reasonably well for daytime because the temperature was not exceeded, did not exceed the set point often. But also that indoor cutoff was effective at nighttime. However, it's possible that readjusting the curve downward for nighttime might have achieved similar savings without indoor cutoff, and that we have not tested. So I'm going to turn it back over to Hugh, who I think is back online, to discuss the nighttime setback results. Hugh, are you back with us again?
Yes, I am. Yeah, thanks. Yeah, so we also looked at the concept of nighttime setback. So that's basically taking the outdoor air reset strategy and having it all drop by 5 degrees at night. And so actually, so the graph actually shows the blue line shows the nighttime setback, and actually the line should not go below 110. But we basically shift to the right. So the blue line is shifting to the right of the green line, and we tried this with a 10-degree drop at night then we had some concerns we might be affecting the comfort of the occupants, so we changed eventually to a 5-degree setback at night. Can we go to the next slide, Jordan? And we toggled back and forth and tried these strategies, and you can see the schedule of what we did here for throughout 2012 and 2013. And go on to the next one, Jordan. And so what we saw really was nighttime setback really did not have much impact. So we could not discern an impact or a difference in gas use. So it's sort of, so we're kind of a believer that and we're also the concern about the nighttime setback is it's an apartment. People have different schedules in the building, so it probably is better to kind of to have strategies that don't change in terms of time, but do things in terms of temperature in the space and outdoors, just as kind of Jordan has talked about. So the next slide, Jordan. Yeah, so kind of the takeaways, and I guess Jordan and I can do this, but that's, so basically we found that outdoor reset has been around for a while, and the parameters matter. And one kind of practical thing we found is that in these controllers get installed, but often the parameters that get put in there are somewhat arbitrary and can be disabled across time. And so it's really important to have those outdoor reset curves set to kind of a reasonable level. And as Jordan has showed, the indoor cutoff is, or to take the information on the space temperatures with the wireless sensors can be a pretty effective strategy. Nighttime setback, we weren't as impressed with the impact that we saw with that, and it didn't really seem to be very effective. You want to say anything else, Jordan?
No, I think that covers it. Thank you.
Okay.
Next up is Peter and Russell.
Hi, this is Russell Roosh and Peter Ludwood from Elevate Energy. Yeah, just wanted to thank Gil and Heather for setting this up. Thank you for your assistance. So we both work for a nonprofit program called Elevate Energy, based out of Chicago. And our buildings program is focused around being a sort of one-stop shop for building owners who are interested in doing energy efficiency retrofits. Sort of guide them through the process from doing the energy audit to presenting them with a report with cost-effective recommendations, helping them with financing, construction oversight, and then ongoing savings monitoring and reporting. We've retrofitted over 17,000 units at this point. And we are one of the organizations that's working with GTI on PAR, the Partnership for Advanced Residential Retrofit. And we're going to be talking about a couple of the studies we've done as part of PAR for Building America. So yeah, just to sort of set the stage, over half of cold climate multifamily units are heated by central steam or hydronic systems. And around Chicago, at least 2/3 of the residential units were built before 1980. So they're rarely designed for energy efficiency. And in our climate zone, heating energy accounts for the majority of residential energy use. So the big question is how to cost effectively retrofit and optimize these older steam and hydronic systems so they use less heat and fuel. Thought it'd be helpful to sort of go through a bit of a primer on how steam works before talking about how we can optimize these systems so they're more balanced. Steam was the best option for buildings constructed around 1900 to 1930. And there's a lot of buildings in Chicago, at least, from that era that still had steam systems that, been converted from coal to natural gas and maybe had their boilers replaced, but their distribution systems are largely the same, and they're not designed for efficiency. Basically, the way they work is control calls for heat, the boiler kicks on, heats water, generates steam, and the steam moves through the mainline pipes, which are initially filled with air, heating the metal and the radiators, and pushing air out through vents on the main lines and the radiators. And then within each radiator, the steam condenses and releases its heat, latent heat, allowing more steam to enter. As the building is heated according to the set point temperature, the boiler shuts off, the radiators cool, the air vents open, and allow air to re-enter the system. So having those vents on the radiators and the main lines open and able to allow air in and out of the system is very important for allowing steam to flow through the building. Here's just some IR pictures of how that looks in the boiler room, and you can see basically the boiler coming on, starts out cool, and then by half an hour the steam has reached the mainline vent and heated up. And that's how this looks in the radiator. You can see the steam sort of traveling through the radiator over time. And again, it's crucial that those vents be open for that to work. So here are some sort of common scenarios we see in these older multifamily buildings that are preventing steam getting through the system easily. You'll see painted over radiator vents, rusted mainline air vents, or rusted or blocked. And then oftentimes the boiler will just be run on a timer which tells the boiler basically to come on during certain parts of the day, but isn't controlled necessarily by the outdoor-indoor temperatures. So addressing these things is going to be a big part of what we call steam balancing. Yeah, as Jordan and Hugh touched on, a lot of these buildings are overheated. Usually what's going on is some units are underheated for various reasons, and then the set point or the timer is set so that the boiler is heating the entire building hot enough so that just those units are satisfied, but that consequently causes a lot of other units to be overheated, which obviously costs a lot of heating fuel and costs money. It also is a big cause of tenant discomfort, which is, so basically we're looking at sort of utility savings and tenant comfort issues when we're talking about balancing. Unfortunately, there are some market barriers to steam balancing that we have to address, and that's sort of what our study was originally written to identify and address. There's really lacking knowledge about how these things work in the marketplace. It's often not offered as a service by contractors or recommended as a measure. A lot of utilities don't recognize it as something which saves energy. It's not really a very easy plug-and-play sort of retrofit. You have to spend some time looking at the steam loops, timing them, and seeing, you know, where the issues are, sort of considering the configuration of the building and the loops throughout the building. And yeah, for all those reasons, it can be difficult to convince owners of the value of doing it. It's a separate issue from boiler replacement. And then, of course, there's always the perennial problem of natural gas being relatively cheap, so it's not always considered worth time or effort. So this is our study. We wanted to figure out how steam balancing measures would affect temperatures in units, how the boiler cycled, and the overall gas consumption of the building. And we did that by installing hobo loggers in 10 steam buildings and then taking a look at their performance before and after retrofit. On average, we found about 10% savings off the heating load from doing these steam balancing measures at an average cost of about $9,800 with a payback of 5.1 years. And the measures we were especially looking at were replacing radiator vents, adding or improving the mainline air venting, and then improving the controls. So we would be replacing timers on boiler systems with those indoor averaging controls that ideally had sensors in about a quarter of a unit or more. And here you can see the results from that study in natural gas use for the 10 buildings. In 8 of the 10 buildings, natural gas use dropped as a result of the measures. You can see the spread of temperatures really decreasing after retrofit. And basically, we had sort of 3 big conclusions in general about steam balancing. One, it is it's an iterative, multi-stage process. You really have to have a conversation with the building manager, tenants, and really take a close look at temperature data before you start, swapping out vents or considering resizing risers or header piping. It's really important to consider the building layout, the piping configuration, and the locations of the units, which are over or underheated. And then again, the cooperation of tenants and building managers is really crucial. It's really important to explain to tenants how, for example, using space heaters can drive up the temperature in their units, and that can interfere with the indoor temperature averaging systems, which control the boiler. And of course, building managers should be properly instructed on how to use those controls once you put them in, because they are, a bit more complicated than just the timers. So that was our steam balancing study. We tried to do a similar approach with hydronic buildings, see if, we could see sort of how much of an issue imbalance was in hydronic buildings, and what sort of measures we could use to address that. So yeah, we wanted to take a look at the temperatures, both within units and across the building, think about what sort of cost-effective balancing strategies we could have. Part of the study was surveying the literature, and then we chose 2 test buildings where we installed hobo loggers and added pump capacity in one of the buildings. We found a really astounding result in one building where there was an instantaneous temperature spread of 48 degrees, and we were able to reduce the average spread in the building over the heating season by 6.5 degrees. Just to give you a sort of sense of the balancing issues in the building here, this is test building A. The boiler is right in the middle there, and there are 2 loofs going to the west and east portions of the building. This was originally a steam building that was converted to hydronic in the 1990s. And when they did the project, they unfortunately undersized the pipes. So there was really a chronic underheating issue to those west units, 56, 57, down to 56, 53. And our retrofit was to increase the pump capacity and see if that would improve the underheating in those units. There was already a temperature averaging control system that had, I think, 8 sensors throughout the building, but unfortunately, because some of the units were underheated, tenants were resorting to supplemental heating sources, which again was interfering with the controls and causing the boiler to kick on less often than it needed to. So here's the temperature data we collected with the hobo loggers. There's some really extreme temperature peaks, and we believe that those occurred because of supplemental heating sources like oven ranges in those units. And while that wasn't eliminated entirely after installing the pump, you do see those go down, and the average spread also decreased. Here's an example unit where you can see some of those extreme temperature spikes before retrofit, and then that lessening afterwards, despite the same. The top line is the indoor temperature, and the bottom line is outdoor temperature. And yeah, we really saw an improvement in the balance of temperatures before and after retrofit. There were 17% of the time the building had a temperature spread of over 30 degrees before retrofit. That decreased greatly down to about 1%. And about 25% of the time before retrofit, the building spread was under 15 degrees. That increased greatly to 52% after retrofit. The other building we looked at as part of that hydronic project was a 1960s two-story building that had underfloor radiant heating, and each unit zoned with a thermostat. That was interesting to see. It was interesting to see that there was an overheating issue on the first floor, despite there being unit zone controls. Some of the units weren't able to really bring the temperatures down in their units, despite having their temperatures set at, say, 65 degrees. They'd be getting temperatures at 75 or 78 degrees. Here's a table that sort of summarizes that. You can see, for example, in Unit 4, which is on the first floor, they had their set point when we came in at 60 degrees, and the actual temperature recorded was 83 degrees. So this was just really interesting to us in terms of collecting very high quality, high resolution data with Hobo loggers that sort of showed a real balance issue in hydronic buildings. It was something we knew about with steam buildings, but wasn't so well documented in hydronics. So again, yeah, our conclusions from that study, sort of in general, were that hydronic buildings can be extremely imbalanced. The unit temperatures can range by as much as 48 degrees. And that could be caused by open windows or intermittent supplemental heating sources. And again, as with steam, when there are zones serving multiple units, it's not zoned by unit, there's bound to be significant variation in temperatures across the building. And then even in buildings where ostensibly there's zone control for each unit, as with the second building we looked at, you can have variations from the set point that are pretty considerable. The causes of imbalance in hydronics are a lot more diverse than in steam. You can have issues with undersized piping, undersized circulators, zone valves that aren't functioning, damaged heat emitters, poor air elimination, balancing valves that aren't configured properly. But still, many of the same lessons from steam balancing apply. So it's really an iterative process where you have to consider carefully the loop configurations and the layout of the building. And again, communication with the tenants and the building owner is really crucial to being able to have the access and cooperation that you need to balance the building. And that's it.
Thank you, Peter and Russell. And Jordan and Eric will be up next.
Great, thank you. This is Jordan again. This presentation is on a thermostatic radiator valve evaluation study. And we're going to review briefly some past research on TRV effectiveness and just talk about how TRVs work, and present the results of a field test to evaluate the effectiveness of TRVs on a steam-heated building with convectors, and then also discuss the impact on heating energy use for a building that underwent a TRV retrofit. So, some background, as we've been discussing, many centrally heated steam and hot water buildings, there's imperfect distribution resulting in wide temperature variations among apartments, and the heating system is forced to supply a minimum amount of heat or temperature to the coolest apartments, and other apartments become overheated. So thermostatic radiator valves, or TRVs, offer a possible solution by controlling heat emitted from radiators based on the temperature in the room. However, in our experience and research, implementation of TRVs in existing multifamily buildings is somewhat spotty. because of cost and also lack of confidence among some in their ability to deliver energy savings. Published independent studies demonstrating their effectiveness is not widespread, with at least one notable exception that I'll discuss. But first, here's a TRV. This is for a one-pipe steam system, which is what was used in our study. It consists of a valve body, a thermostatic operator that senses the temperature of the room, and an air vent. So with a TRV in place, when the room reaches set point, the valve closes, preventing air from escaping through the vent, and thereby preventing new steam from entering the radiator. And Eric will talk a bit later about the implications of this cycle with convectors. So as I mentioned, we only found a few studies on field work and field evaluations of TRVs, even though TRVs have been around for many years, 50, 60 years or longer. We're somewhat surprised at this. This is a list of the studies that we were able to locate. The most notable was an extensive 1995 study sponsored by the New York State Energy Research and Development Authority, or NYSERDA, in which TRVs were installed in a number of buildings using one-pipe steam primarily, and most of those with standing radiators. And that study determined that they were saving about 15% of energy after implementing those measures. Most of these other studies are either modeling or not specific to one-pipe steam implementation. So despite that one research study, there's a range of opinions in the market, in our experience. And so we decided to talk to a number of people in the industry about their perception of TRVs and found a wide range of opinions, everything from we swear by them to we don't believe they work in one-pipe steam. And this was from engineers and others who are active in the industry. Some other common themes included that the perception that steam cycles cause TRVs seals to fail early, and that apartment level control provides basically a psychological boost, but there's not much change in temperature with TRVs. So the next step that we decided to undertake was a small field test to look at some of these issues in the real world. So I'm going to turn the presentation over now to Eric, and he's going to discuss this field test.
Thank you, Jordan. So the main objective for the experiment was to get detailed space temperature and radiator temperature data at the apartment level, both before and after TRV installation, and from this determine if the TRVs would operate as expected and if they would control space temperature well. A second objective was to test old TRVs alongside new ones and see if their performance differed. So in this case, the valve bodies that we used for the older TRVs had already been in service for a number of years in a different installation. And the sensor and thermostatic operators were previously unused, but they were older and the moving parts had, while in the packaging, still been subject to normal space temperature fluctuations. So the apartments that we experimented with had similar layouts, orientation, size, distribution system, as was said, was one-pipe steam with convectors. And the TRVs had been installed over the preceding summer throughout the building. But these two apartments received their TRVs in mid-January so that we could collect pre- and post-installation data. And as Jordan mentioned, specifically with one-pipe TRVs, there's a key difference in their application versus a two-pipe steam system. With two-pipe steam, the TRV can go at the radiator inlet, and this allows it to block the steam entirely from entering the radiator when the TRV is closed. But with a one-pipe steam application, the TRVs are installed to the vent side of the radiator, partially because of debris and condensate clocking issues at the inlet,
and also because of the lower cost associated with smaller fittings and easier access at the vent end. So a one-pipe TRV in this position can work in either of two ways. One, if the space temperature has already satisfied the sensor and the TRV is closed before a steam cycle begins, it can prevent the entire volume of air in the radiator from exiting the radiator body. The cycle runs, and no heat is going to be added to the space. Or two, if the TRV is open at the beginning of the steam cycle and closes when the air has only been partly displaced from the radiator body, in this way, it can effectively limit the volume of that body that receives steam over the duration of the cycle. And you could think of effectively as a smaller radiator. So the factors listed here on the slide govern those two competing time frames that have to overlap in order for a TRV to limit heat added to the space in the second scenario. Once a steam cycle begins, the TRV sensor has to actuate the valve in a shorter time span than that in which the air is displaced. With a large cast iron radiator, that can take 8 to 10 minutes for it to fill completely with steam. But with convectors, as we have in this building, they're going to fill in 2 minutes or less. So the manufacturers of the TRVs recommend venting the steam mains and risers aggressively and using small air vents on the radiators themselves so that fill time can be extended to as long as possible, giving the TRV more time to respond to the space temperature. And the pressure at which the steam is delivered is also going to affect that fill time a little bit. So the reaction of the TRV has to happen in less than 10 minutes for a cast iron radiator and less than 2 minutes for convectors. So this is sort of a toughest case scenario that we're using TRVs on both one pipe steam and with convectors. And just going to that last point of the TRV reaction, the sensor depends a little bit on the rate of expansion of the sensor material, but even more on the establishment of a convection current and where the sensor is when it gets bathed in that current. And lastly, the set point, the TRV might well be a little different from your desired temperature, space temperature. So this graph shows the data that we collected, and just give you an idea of what we're looking at. This is for all 6 channels, all 6 sensor channels over a 2-day period in January. That blue line at the bottom is the outdoor temperature, and you can see that bottom trough in the far right, that's the polar vortex that we experienced this winter. Space temperature is the orange line that extends across the middle. It's kind of mid-60s, mid-70s in the apartment for the time period. And the blue, red, and green lines, respectively, those are indicating the temperatures of the radiator inlet, midpoint, and valve end. So from left to right, you can see how during that evening of the 6th, the boiler doesn't run, and then there's regular hourly cycles for the course of the next day. The beginning of the 7th, there's that's a morning boost cycle that you're looking at, and then you see the cycles are the bands are thicker, so the cycles are longer on the 7th because it's a much colder day, which is what we expect. And the purple line, lastly, that's the near window temperature. So you can see what look like window opening events where it drops suddenly and gets erratic. There on the 6th, and there's a shorter one on the 7th. So let's take a look at the results. So here you have space temperature averages for each room in the 2 apartments, both before and after the TRVs are installed. And there are a few things worth noting here. One, it's desirable to only consider space temperatures for this when the tenants have their windows closed. So we filtered out the data where the near window temperature was below 55 degrees. And in apartment 1F, we actually noticed that the tenants were opening the windows much more frequently, and that might have mitigated the impact of the TRVs there somewhat. Also, the kitchens, they're weighted equally here with the other rooms, even though they have much higher internal loads and relatively small square footage. And lastly, the apartments, they weren't incredibly overheated beforehand. So this raises the question, are TRVs meant to achieve temperature control down to 1 or 2 degrees, or are they better used in applications where the goal is to limit more severe overheating? In the next 2 slides, I want to show you other aspects of the heating system performance that we kind of uncovered through the data that may have also affected the results. So these temperatures show average post-TRV installation space temperatures that occurred when outdoor temperatures were relatively mild, and that's between 35 and 50 degrees here, and when they were severe, which was between 10 and 25 degrees Fahrenheit, alongside the standard deviation for each of those subsets. What we were looking for was to see perhaps if space temperature swings would be greater in one case or the other, and that would be due to the TRV performance. But what we saw, and what we might be seeing here, is that might be that the slope of the outdoor reset boiler control wasn't matching the rate of heat loss experienced by the building in mild and severe cold. The couple that sleeps in the master bedroom in apartment 1F, they complained specifically that both before and after the TRVs were installed, on very cold outdoor days, they were cold in their bedroom. And furthermore, you notice that the space temperature swings, kind of represented by the deviations, were nearly constant within the apartment from mild to severe cold outdoor conditions, but they varied between the two apartments. And again, that might have to do with the tendency of the tenants in 1F to open their windows more often. The next slide. This graph shows the data for one room, the living room in apartment 1F, for a few days immediately before and after TRV installation. And you can see in the days leading up, and this was the case for the entire the heating season before we installed the TRV in this apartment, in this unit, in this room, that the radiator never really got hot. Whereas as soon as it was installed, you can see consistent heating cycles, and this could very well have to do with the replacement of the air vent that happened at the same time the TRV was installed. And it might be that this room wasn't getting the heat until it happened, and indicating some imbalance. In the next slide, we're going to look at the gas heating bills for the property for the entire building over the past 2 winters to get an idea of how the building-wide TRV installation affected fuel consumption. So this graph shows therms of space heating use per day against average outdoor temperature for the corresponding bill periods. Orange represents the winter before the TRVs were installed, and the blue is that first winter with the TRVs in each apartment. Baseload usage was approximated by non-heating season use and subtracted out to just yield heating fuel consumption here. And you can see that the data points are very close, and doesn't really indicate from this that they're using less fuel. So our conclusions are, at the building-wide level, we're not seeing a very measurable fuel savings, and at the apartment space temperature level, it's somewhat ambiguous, with 1A gaining a few degrees, lowering a few degrees space temperature, 1F seeing the opposite. And the possible reasons for this might include that the distribution venting may need balancing, or the venting might be inadequate, and that was not done before the study was implemented. The boiler outdoor reset curve on the heat timer that controlled the boiler for this building was set to I both before and after the TRVs were installed. So that wasn't adjusted, and maybe that needed to come down once the TRVs were installed. And the tenants are still, the behavior hasn't caught up. They're still opening their windows very regularly. Also not listed here, but we talked a little bit before about with one-pipe steam and with convectors especially, the TRVs have a very limited window of time in which they can respond to space temperature. So that's a tougher scenario for them to perform. And that's our results. We'll be holding a one-day meeting in New York City later this year to present and discuss findings from this and other related research on multifamily central system retrofits. Please contact us if you're interested in attending, in person or on the web. And thank you.
Thank you to the panelists for those outstanding presentations. And we have time now for a few questions. We already have some great questions from the audience, and you may submit additional questions through the questions pane on your screen. The speakers will answer as many as time allows. So we have a few questions targeted to Jordan and Hugh's presentation. The first one is, could the nighttime setback have been made effective if it was set more aggressively?
Yeah, so this is Hugh. I guess I'll take that one. Yeah, so we did try a 10-degree setback for a while, and we. Hello? Everybody can still hear me? So we did try a bigger setback, and we were concerned there was some in that building. There was some tenants that worked the night shift, or had an offset schedule, so they were up at night. And we had a little bit of feedback that there might have been a problem, so that's why we had backed off on that. Jordan, do you have anything to add?
No, that I think covers it.
Okay, and then the next question for you two is, are the boilers in Building 4 condensing or non-condensing? This audience member was worried about a non-condensing boiler operating with return temperatures lower than 130 degrees.
Yeah, so it turns out that in Building 55 they did have they were both non-condensing. In Building 55 they did have a bypass valve that held the temperature higher. On Building 4 we were also concerned about that. And after kind of monitoring things and working with the on-site contractor who was in charge of the building, we kind of came to a mutual conclusion that we were going to be okay at 110. But that is a concern that a non-condensing boiler, you shouldn't go below 130. Jordan, anything else to add to that?
The only other point is that the boilers did have condensate drains, so that there was some anticipation by the manufacturer that they would experience some condensation.
Yeah, and we did, and I don't believe we ever saw any evidence that there was consistent condensation. So those drains, of course, are for startup, but yeah, we didn't see any evidence that had been continuously a problem when we had it 110.
Okay, thank you. And then we have a couple of questions for Peter and Russell. Can you provide a bit more information about the logistics of steam loop timing?
Sure. Let me pull up a slide here real quick. Can you kick the screen over to us?
I'm sorry, was that Russell?
Sorry, can you have my screen be showing?
Yes, is that Russell or Jordan? I'm sorry.
Sorry, this is Russell.
Okay, thank you. One moment, please.
Thank you.
There you go. It's coming back. Thanks.
Great, thank you. So yeah, to time steam loops, which you would do in order to figure out which loops in the building are getting heated faster than other ones. The goal being to even them out so that the loops are more or less getting heated at the same time, so that the loops that are getting heated more quickly are not overheating, and the loops that are taking longer are not underheating. To do that, you would need IR cameras, photographic cameras, stopwatches, just like a sketch pad for diagramming. And then usually you'd want to do it having multiple auditors taking a look at multiple steam loops at once, assuming that you can't do it all yourself in the boiler room. So that would be in the case where the mainline vents are distributed around the basement and are not just all contained in one room. Basically, the procedure would be to have the building owner shut off the boiler before you get there, and then walk around and diagram the loops and vents. Then you would have yourself or you and however many other assistants you have with you train your IR cameras onto the mainline vents, and taking photos as you turn on the boiler and sort of watch to see the temperatures increase. And then you just basically use a stopwatch and time it until they reach 200 degrees. sort of record the times for each and then compare. So it's a good diagnostic for figuring out, which loops need more venting, whether it's placing the vent, increasing the size of the vent, or repositioning it. Yeah, that's basically your starting point for steam balancing. You have anything to add, Peter?
Nope.
Yep.
Okay, thank you. There was another question for you too. Any use of buffer tanks in the hydronic-based heating systems that were noted to have lower temps?
I'm sorry, was that question for us at Elevate?
Yes.
Could you repeat it, please?
The question is, any use of buffer tanks in the hydronic-based heating systems that were noted to have lower temps?
I'm not sure exactly what they mean by buffer tanks. Could you clarify?
Expansion tank?
You mean an expansion tank for air?
Yes.
Yeah, the question is whether we replaced the air tank. We did not. There was sufficient, the air tank was sized appropriately and was working in the hydronic building that we retrofitted with the new pump.
Okay. And then there's a question for Jordan and Eric about the TRV. And that is, how is the building performing before the TRVs were installed compared to similar properties? Was it especially inefficient in terms of heating?
Well, we looked at, for both before and after, the average BTUs per square foot per heating degree day, and that was about 10 BTUs per square foot per heating for HDD, which is not excellent. So maybe, average performing, a little bit lower than that. And we don't have building-wide space temperature just for those two apartments, but the overheating wasn't egregious, but certainly present.
And then there was another question for Jordan and Eric. Are there any research results on limit point landlord TRV savings?
The TRVs in this building were effectively limited because the controller that was inside the radiator enclosure, so it's unlikely tenants were going in there to adjust them, but they weren't physically limited. If you wanted to, you could go in and change that. And I'm not aware of any research on savings as a result of specifically that. The TRVs that we installed in apartments 1A and 1F were locked to 3 1/3 on the valve, which is on the dial, which correlates with about 70 degrees. Else you want to add to that, Eric?
No.
Okay, and then there was another question regarding the TRVs. Are there faster responding thermostat valves that would work better?
So the variables that we were able to consider, or that I'm aware of, include the sensor fill, what goes in the capillary tube, whether it's a wax that changes phase or some kind of liquid or gas. And I think, a gas is the fastest, and the response time is something, I think, within a second or something like that. But, the other variable was where the sensor is placed. And the manufacturer recommended, in this case, that we put it, in the at the bottom of the convector where it would receive that incoming convection current. And what actually happened in the building was the plumber installed, for the other apartments that were not part of our specific test, he installed that sensor next to the radiator, which may have, it might have experienced slightly cooler or warmer temperatures since it was a little bit higher up on the wall. And that might have more of an effect than the response time of the sensor itself, which is on the order of a second, whereas that convection current might take a couple minutes to establish. So I think that's the place to look for. If we were going to do it again or try to improve this installation, is where the sensor goes in the room.
Okay. And another question for the TRV study. What pressure was the boiler running at? Is it possible that the TRVs were overwhelmed by pressure? Most are limited to systems with 2 psi or less.
We were there a couple weeks ago. I believe they were set, I'm pretty sure they were somewhere between 2 and 4 psi. And that is greater than what you're saying at 2. I don't have a definitive answer. I think they were higher. I'm pretty sure they were higher than 2 psi. The boiler was set at higher than 2 psi. That's a good question.
Okay. Thank you, everyone. And panelists, before we take our survey, do you have any additional or closing remarks you'd like to make?
Well, this is Peter and Russ. We just wanted to thank you again for organizing it, and certainly if folks would like to talk more offline, we'd be more than happy to do that. And also just thank the folks from Levy Partnership and you for doing the presentation with us.
This is Jordan. Likewise, thank you for organizing it, and it's been a pleasure to be a part of the webinar.
Yeah, and this is Hugh Henderson at CDH. We're happy to be involved too. Thanks.
Well, thank you for your participation. And now we'd like to ask our audience to answer 3 short questions about today's webinar. Your feedback will help us to know what we are doing well and where we can improve. Heather, will you please show the first question? Okay, the first question asks whether the webinar content was useful and informative. To answer, you can click on the radio button right in the GoToWebinar panel. Okay, thank you. The next question asks about the effectiveness of the webinar, of the presenters. Excuse me. And the next question, the third question asks whether the webinar met your expectations. Thank you for taking our survey. Stay tuned for the next Building America webinar on August 13th at 3 p.m. Eastern. This webinar continues our series on high-performance building enclosures and will focus on effective strategies to address moisture and thermal needs of building envelopes. On behalf of the Building America program, I'd like to thank all of our expert panelists for their time today and to our attendees for participating in today's webinar. We've had a terrific audience, and we very much appreciate your time. Please visit the Building America website to download a copy of the slides and learn more about the program. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar.